just moved it to a different space in 3 dimensions where you can easily separate. So latent space is something similar. You take some data, you transform it into some other dimension, and where these things go, like those red dots went here, the triangles went to the lower half, we don't know where they will go in latent space because we can't follow each of the network paths, and it's cumbersome to see where each of these data points will go. So, but just understand that when we say latent space, it's nothing but some operation, some function being applied to your input data to transform it somehow that we don't fully understand. So what we want to do is we want to take some known distribution. For example, normal distribution, that is the most well known. And we want to move it closer and closer so that our latent space is now transformed. So we got data transformed into latent space, and we want to transform the latent space into a normal distribution. And once we do that, then we can use that equation of the normal distribution to sample from it directly. So what we can do is we can treat this x and y as mu and sigma of a normal distribution. So again, mu was the mean and sigma was the standard deviation. And we can just assume that it is that, what is coming out of this network. And then we can sample from it, right? And given a sample, we can tell its probability because we know the formula, and then we can interpolate between samples and do all kinds of things. So how we set this up for training is we assume this output is mu and sigma, and then we sample from it and we get a result, and then we compare that to the input image. So now we have 2 losses. So one is trying to take the latent space to a normal distribution, and we can use the KL divergence loss for that. And then we have a second loss, which is trying to take this data that we just moved to the normal distribution and trying to take this back into latent space and then trying to recover the data itself. So there is this thing, the content loss or the reconstruction loss and the KL divergence loss. So that is something called a variational autoencoder. So this was one of the earliest generative models that was made. It's very cool, and a lot of other models use something similar. And so imagine that. So now you take your data, push it through your network, you get the mu and the sigma out, you sample from, assume that it's a normal distribution, and sample from that, and at the same time, you compare the loss for this content, and then you also have the scale divergence where you're trying to minimize the difference between normal distribution and whatever distribution the latent space is in. So that looks pretty cool. So now this is a visualization of a variational and autoencoder where you can see all these digits we trained. Normally this is in some high level dimensional space, but there is a process. If you go to the site projector.tensorflow.org, it has some nice visualizations. There's a process to convert this into a 3-dimensional data using some PCE-like process, and then you can visualize them. You can see that all the similar digits are kind of close to each other, and they're all clustered around things, and things that are kind of not separable easily, they are intermingled. And there are some other better methods. If you did the KL divergence properly, they will also kind of nicely separate out. And this allows us to do all kinds of different generation. You have, in this particular example, you have a set of images on the left column and the rightmost column, and then you can interpolate between the two. So you have, because you choose some sigma and some mu, and then you choose something near it, and then you can just, you have a sigma and a mu for each of those extreme portraits, and then you just interpolate between the two. And you can do it crossways, you can do multiple interpolations, and it works pretty well. All right, so we're up for a 10-minute break, and please come back. Or we're going to go into transformers next. Mia will cover transformers for the next hour. And if you're leaving, you can grab a note card.
And grab more if you want. Hello again. again, I am Mia, and I'm a graduate student in computer science at Stanford University. And today I will be talking about large language models, which is, I believe, a really important area of generative machine learning to have an understanding of. So we will begin with talking about general AI chatbots and quickly dive into some model architectures that people use for these NLP tasks with a focus on transformers. So I believe many people here have integrated the use of these AI chatbots into their daily workflow for various tasks such as proofreading and editing your text, drafting an email, debugging your code, or explaining some difficult concept. These apps have similar interfaces that allow you to have conversations through text queries, and many of them have also incorporated multimodal inputs such as images and files. Today, we will focus on text query and text output from these large language models. Now, let's think about what happens when you input a text prompt into such an interface. As users, we input some text in the interface, which then gets processed by a machine learning model. This computation happens in the backend of the interface we interact with. The ML model will spit out an output, which then gets displayed on the interface. So we can continue this interaction for as long as we want. And this user interaction is not new. Then what was ChatGPT's secret to success? Well, the winner here is the machine learning model behind ChatGPT, which is called GPT-4. We can replace the ML model behind the interface and have similar interactions. For example, for Google's chatbot Bard, the underlying model is called Gemini. So all popular AI chatbots have different ML models that are trained in slightly different ways. But in its essence, they are mappings of input to output. Or you can imagine the ML model as a little robot who will write down the responses given some input. So the question becomes, how did we arrive at where we are today with the impressive performances and what is actually going on under the hood of text generation? To realize how far we have came, let's take a brief history detour. Here is an overview of the history of large language models. ChatGPT is not the first ever chatbot, even though it definitely is one of the most famous and far-reaching chatbots of all times. The first chatbot actually existed from the year of 1967. ELIZA was developed in the 1960s at MIT. It is a very early natural language processing program. It functioned as a basic chatbot mimicking conversation using pattern matching and substitution. Its most famous script, Doctor, simulates a psychotherapist. It does by examining the text for keywords and then transforming the input into an output response. Here in this interaction, we see that when user says, "Everything bothers me lately," ELIZA replies with, "Does talking about this bother you?" And when user says, "Are you here to help me or not?" ELIZA replies with, "Why are you interested in whether I am here to help you or not?" We can see that ELIZA's responses do seem like a reasonable follow-up to the user's input, but it can quickly become frustrating as it lacks creativity to branch out from the user's input. Here is a modern website that implemented ELIZA with some tweaks. You can try talking to ELIZA at this URL. It was also featured in an episode of Young Sheldon, where Sheldon became enamored with the program but soon realized its limitations. So without machine learning, there's only so much we can do with rephrasing an input using pattern matching. The second major breakthrough in the history of large language models is LSTM. LSTM is a type of neural network which belongs to the family of neural networks called RNN. RNN stands for recurrent neural network. So compared to the normal sequence network that you see here, RNN adds a loop from the input to output. And this loop allows information to be passed from one step of the network to the next. A RNN can be thought of as multiple copies of the same network, each passing a message to a successor. This diagram here shows what happens when we unroll the loop. The problem with RNN is that sometimes the gap between the relevant information and the point where it is needed becomes very large. We could theoretically manually pick information from certain time steps and pass it down, but that's just not feasible in practice. Therefore, we need something more than just a simple loop. hence the necessity of having the architecture LSTM. They are a special kind of RNN capable of learning long-term dependencies. The intuition here is that LSTM has a way to select what information to keep and pass down and what information to discard. Let's see a case where having LSTM's ability to remember and utilize information over long periods is key. Let's bring up a meerkat who really likes to talk. So the meerkat goes on and on about the life of a meerkat. At the very beginning of their monologue, the meerkat begins with, "Hello there, I'm a little meerkat. My name is Steven." This is a very nice piece of information that a chatbot can utilize later for a very personal conversation. But if we do not have memory over inputs over time, we will lose that piece of data. And this is just one example of how previous inputs can be useful. Other applications can include maintaining coherence in conversation, understanding user intent, and handling complex tasks. Now we have quickly went over two potential model architectures we can use to build a chatbot. There are many tutorials you can find online that uses RNN or LSTM as the ML model for an AI-powered chatbot. Then why haven't we heard of these chatbots? The answer is that the generated outputs from previous chatbots are simply not as high quality as what we have today. So people couldn't utilize them for various tasks, therefore further highlighting the importance of model architecture improvements. The type of model used by GPT is called transformers, which is what the T stands for in GPT. And quite obviously, we can see that the success of ChatGPT shows how transformers is a much more powerful architecture compared to the previous two. So 20 years after LSTM, the transformer architecture emerged. Here is some more evidence showing the popularity and insane growth of ChatGPT. While it took Instagram 2.5 months and Netflix 3.5 years to reach 1 million users, it took ChatGPT 5 days. And as Harvard Business Review calls it, ChatGPT is a tipping point for AI. There are many aspects to what made ChatGPT so popular, but here are two key factors. First, GPT-4, the backbone of ChatGPT, was trained on 45 gigabytes of data. It's fascinating how much data we have access to nowadays as more people post online, which then can be scraped and stored into a dataset for training. Second, the advancement in the field of machine learning is what made these AI chatbots usable, and that's what we will be focusing on today. So today we will cover the core components of transformers, text generation, and performance improvements with our LHF, which stands for Reinforcement Learning with Human Feedback. We will start by talking about transformers. Transformer is a type of machine learning model, and the core components of any transformers out there are summarized in this diagram. We will cover each individual part starting from parallel neural networks, multi-head self-attention, residual connection, and layer norm. So transformer was proposed in 2017, and it was designed by a group of NLP researchers. It was a continuation of the LSTM neural network architecture, and it outperformed this significantly. First, transformers use parallel neural networks. So instead of processing our input sequence one by one, transformer processes the entire sequence all at once. This makes transformers have impressive speed even when the input sequence is long. The second core feature of a transformer is multi-head self-attention. So imagine if you are reading a book. When you read, you don't pay attention to every single word equally. And instead, you focus on certain words more than others to understand the meaning of the sentences. For example, in the sentence, "The meerkats love watermelons," you might focus more on meerkats and watermelons to get the main idea. The attention mechanism in transformers work in a similar way. When a transformer model is processing a sentence, it doesn't treat all parts of the sequence equally. Instead, it focuses more on the important parts that are relevant to understanding the meaning. So our goal here is, given an input sequence, we want to attend to different parts of the sequence. But before that, first we need to look at how do we work with raw text. Given the text sequence, we wish to convert it into a meaningful numerical representation that computers can easily work with. Here we introduce the tokenizer. Tokenizer breaks down text into smaller manageable pieces called tokens. There are many types of tokenizers we can use, the most simple one being character-based, which means we slice the input sequence into smaller tokens by breaking up the characters. Another strategy is tokenizing every individual word by splitting on spaces or punctuation. A more involved tokenization strategy is subword-based. It relies on the principle that frequently used words should not be split into smaller subwords, but rare words should be decomposed into meaningful subwords. These subwords end up providing a lot of semantic meaning. So the whole purpose of tokenization is to create a vocabulary from a corpus. And a corpus is simply a collection of text, such as data set we use to train an NLP model. And a vocabulary is the set of unique tokens found within the corpus. Each token will have a specific numerical ID that we can look up in the vocabulary to find the corresponding token. Here are some actual code you can use to tokenize an input text sequence. So we first load a pre-trained tokenizer and retrieve the tokens. We can further convert the tokens into their corresponding IDs from the vocabulary, which can then be reconstructed back into the input sequence. After getting the token IDs by constructing our vocabulary, we actually want to map these token IDs to n-dimensional vectors that we refer to as embeddings. This mapping between token ID and embedding is learned. So normally you would just apply a pre-trained model to do that for you. And here's another code snippet where we tokenize the input and then use a pre-trained model for getting the embeddings. And you might ask, why do we need these embeddings? Aren't the IDs already numerical representations of our input data? Well, the main motivation here is that given any word, we wish to have a way to determine its relationship with any other word. For example, the word meerkat and monkey should be pretty closely related, whereas the word latte is unrelated to both of them. So the IDs from the vocabularies are not going to be semantically meaningful, and we cannot compute similarity or alignment with these IDs. Therefore, we wish to have a meaningful vector representation of words, since we can easily calculate distances and alignment between vectors. So here, suppose our vocabulary has only 5 words: king, queen, man, woman, and child. We could encode the word queen as the following. We flip a 1 at the index where we have queen in the vocabulary. But using such an encoding, there's no meaningful comparison we can make. We can only determine if 2 embeddings are the same. So we have to come up with some new ways to numerically describe any given word that allows interesting comparisons. Now let's think about assigning weights to elements of a word. So instead of a 1-to-1 mapping between an element in the vector and a word, the representation of a word is spread across all of the elements in the vector, and each element in the vector contributes to the definition of many words. For example, with the same vocabulary of king, queen, woman, there are several axes we can use to differentiate these words, such as royalty, masculinity, age, and such. So these can be used as entries of the embedding vector, where we give different weights to different axes for each word. The word king will have a lot higher value in the entry for masculinity compared to queen, while both of them will have high values in the entry for royalty. With these high-dimensional vectors, we can now do vector manipulations on the words. Here we have the 4 vectors, king, man, queen, and woman. We can compose them like regular vectors, and here we see how king subtracted by man plus woman gives us queen. So the fascinating takeaway here is that we can see text not as a sequence of characters, but as a point in some high-dimensional space that represents its semantics. Now we know that given a text input sequence, we convert them to some text embedding vectors. And just to recap our goal, we wish to attend to certain parts of the input. now we can introduce attention weights. So to pay attention mathematically, we define a scalar value called the attention weight for each individual embedding vector. When we don't define attention weights, we are essentially paying uniform attention to all inputs. Given we have 4 inputs here, we will be paying 100 divided by 4 equals 25% of our attention to each individual input. But let's say now we want to pay the majority of our attention to certain parts of the sequence. We want to attend to the word meerkats and watermelons. Then we will rescale the attention weights so that x2 and x4 have greater attention weights. We can place 40% of our attention to x2, another 40% to x4, and leaving 20% for the rest of the sequence. And now we have an array of values that we can pass along with our input embedding vectors into the model. This turns our input sequence into a weighted sequence. So no matter what kind of operations we end up doing on the sequence, x2 and x4 will have more influence over the output. So far, we have talked about attention from a third-person perspective, which is the regular normal attention. But in transformers, we use self-attention, which just means for each embedding vector in the sequence, we compute attention weights for all other vectors in the same sequence. So we're paying attention to ourselves. Given the input embedded sequence, they are first projected into 3 types of components. So this is how you would actually compute the self-attention in practice. We project it into queries, keys, and values using 3 learned matrices. And these weight matrices are adjusted as model parameters during training. I think the most intuitive way to think about it is think of them as a tool to help us decompose an input sequence into useful components. The most common attention computation is to compute dot product between the Q and K matrices, which is the QK transpose you see in the first purple rectangle here. And computing dot product between vectors always give us a measurement of how similar the 2 vectors are. So this intuitively makes sense, since we normally would want to, for a word in a sequence, we wanted to attend to other words that are similar to itself. So lastly, we get a weighted sequence by multiplying the values with our attention weights. In practice, we also repeat the computation multiple times in parallel. Each of these is called an attention head. So we split its query, key, and value parameters in ways and pass each split independently through a separate head. And all of these similar attention calculations are then combined together to produce a final attention score. This is called multi-head attention and gives the transformer greater power to encode multiple relationships and nuances for each word. To recap what we have just covered, we learned that given the text sequence, we need to perform tokenization and embed these tokens so that we can easily compute self-attention to weight parts of the sequence differently. With each embedding vector in the sequence, we also need to encode their position in the sequence. The position of words are crucial since the 2 sentences here, meerkats love watermelons and watermelons love meerkats, have the same set of words but very different meanings. Therefore, we need to encode each embedding vector's position to have a clear idea on where they locate in the original sequence. And the encoding can be either absolute or relative. The next key component of transformer we will cover is residual connection. We have seen different types of networks that have some input to output mappings with hidden layers. Then it seems like the magic of neural networks is within these layers, so it makes sense to just want to add more layers and expect better results. But unfortunately, that's not the case. Gradients are great, they tell us which direction to go to further improve the model, but as a network depth increases, gradients actually become problematic and resemble white noise. And this problem is called shadow gradient. So if our gradients from our model starts to look super similar to white noise, we are very lost. The model will not be able to further optimize its performances since we don't know which direction to go. So a deeper network might actually never catch up to shallower networks over iterations. Here we introduce residual connections, which is going to help us with bad gradients. It's also a very key component in transformers for stable gradients. Here is a normal sequential connection. We pass down the layer output f1 of x as it is, but in a residual connection, we actually add the input to a layer onto the output of a layer. So instead of passing down f1 of x, we pass down the sum of f1 of x plus x. And now let's do some math to understand why this helps with gradients. It's a pretty interesting thing to look at. So here we have a very tiny network that has residual connections. In the first line, we see that h1 is defined as the sum of input x and f1 of x with some weights. Since we're adding the input to the first layer f1's output, we see that this is a residual connection. And that's the case for all other equations in the system. So each layer has residual connection. And here, y is our final output on the last line. So now we want to unravel the definition of our final output y to only have transformation functions and our original input x. So to do this, we do some simple substitution of all the intermediate values. Beginning with h3, we can replace it with its full definition, h2. And after all those substitutions, we end up with this very gigantic definition of our final output y. Let's take a brief moment and try to find all occurrences of f1 of x. Does anyone have an answer for how many occurrences we have here? We actually have, I think, 7. Oh, I counted wrong, sorry. Yeah, so we actually have 8 of them. And yeah, we like that because when we take the partial derivative of our final output y with respect to our f1 of x, it is equal to a sum of all of these terms. And this sum is good because first we have one identity term and 7 chains of derivatives. So the derivative chains are very short here, and we like that because gradients from shorter path give better results. So now with the help of residual connections that give us better gradients, our meerkats can find their way back and find a better model. So the takeaway here is that gradients are very important for optimization, and we come up with model architecture changes in order to have better gradients. So what are some other solutions and techniques we can use to improve our gradients? One thing is batch normalization. It normalizes the input of each layer for each mini batch during training. This means that for each mini batch of data, the inputs to the layer are normalized to have a mean of 0 and a standard deviation of 1. And doing batch norm reduces shatter gradients, give us more stable forward propagation and regularization. A famous architecture that uses both of these techniques we have just covered is called ResNet. And with the help of all the new things we have just learned, ResNet was able to increase the number of layers and have better results. Lastly, Transformer also utilizes layer norm for good gradients. So layer normalization, very similar to batch norm, but different. It normalizes the input across the features for each individual data point rather than across the mini batch. This means for each data point, the inputs to a layer are normalized to have a mean of 0 and a standard deviation of 1 across all features, independently of other data points in the mini batch. So this can be very helpful in sequence models and other contexts where the size of the mini batch may vary. So here we have it. We have covered all the core components of a transformer model. There are other tricks and little techniques you can add in here and there, but these are the very fundamental core components of any transformer out there. So it has been proven to be extremely high performance, especially for language tasks. Next, we will cover text generation and RLHF. Now we understand the theoretical concepts behind the models, but how do we actually generate long responses that can be useful for the users? If we look closely at how ChatGPT responds, you can notice that it is spitting out one word at a time. And that's actually what happens. Large language models are next word predictors. A transformer trained on text data will spit out probability values for each token in its vocabulary in terms of how likely the token will be the next word. And there are many ways to select the next word given the distribution. By greedy search, we would just pick the word with the highest probability. And there are many other ways to select the next word. For example, beam search is when you choose by looking at a few steps after the current prediction. There are also other sampling techniques to provide more creative outputs. So you can repeat this process again and again and again to get longer outputs by repeatedly finding the next word. And here are some code for loading and generating text using pre-trained language models. So here you first load a tokenizer, and then you load a model. You encode your input to IDs, and then you can ask the model to generate an output. So you can specify different types of search you want to use. And so far, we are assuming that we can accurately capture the entire distribution to perform the search and get the most likely next word. But is that the case in practice? In reality, it is difficult to capture the entire distribution. Take the example here and imagine now we want to generate fish that looks and behaves like it belongs to a very specific river. We can try to capture as many fish as we possibly could from the river and learn from the captured samples. But we will never know if we have enough samples to cover the representative features of the distribution. So the answer is, we definitely try to collect as many data samples as possible, but it's a very difficult task. So to improve our capture distribution, there are several techniques we can use. The most straightforward strategy is to do fine-tuning. With large language models, we do not start with an empty model from scratch. We have a friendly pre-trained model knocking on the door, bringing a set of already existing weights. We can introduce our new problem to the pre-trained model. The new problem should be adjacent to what the pre-trained model already knows. And in order to fine-tune the pre-trained model, meerkats collect new data to demonstrate how desired responses should be. And with this set of smaller data sets, with fine-tuning, some of the existing weights are frozen, while some weights are being changed or added to fit the new data. And here are some actual code to fine-tune a pre-trained model. We always start with cleaning and tokenizing our data. Then we will load the weights for a specific model checkpoint. And we can set up a trainer by defining some evaluation function and some more arguments. But the trainer will take care of optimizing the model with the new data. So GPT was also further improved using RLHF, which stands for Reinforcement Learning with Human Feedback. With RLHF, we begin by asking the model to finish an incomplete sentence that we pass in as a prompt. For example, we can pass in the unfinished sentence, the dog is ... And the model will generate several samples, such as the dog is barking at the neighbor's cat, the dog is exploring its surroundings with enthusiasm, and the dog is friendly, greeting everyone with a wagging tail and a big smile. Next, a human annotator ranks the responses based on some specific criteria. You might have actually participated in this while using ChatGPT. Sometimes it offers you a few possible responses and asks you to choose the best one. With these rankings, we train a reward model that is capable of giving evaluations on how good an input is. And the model is further fine-tuned to optimize reward from the reward model. Here in the illustration, we have candies representing reward values, and the model in blue is being changed while getting candies from the reward model. So that concludes our section on large language models, and we'll see you in 10 minutes.